Welcome. Today in this video we look at section 3.3 Rules of Differentiation. Here we learn some shortcut tricks to taking derivatives. All of these tricks, all of these rules are based off of the definition of the derivative, but we're going to see that we can make our work a lot easier. I'll split this section up, 3.3, into 2 days. Day 1 is the basic rules. I'll just kind of show the rules, and then day 2 we will really spend a lot more time practicing them. Today we will cover 5 rules for taking derivatives. The first rule is the constant rule. A constant actually is a function. I can say I have a function f of x equals 5. So this is a constant function. So f of 2 is 5, f of 17 is 5, f of negative 91.8 is 5, f of anything is 5. It's a constant function. So the derivative of a constant function turns out to be 0. The derivative of a constant is 0. The derivative of 5 is 0. The derivative of negative 5/4 is 0. The derivative of pi is 0. Here's a little graph. It sort of makes sense of why this should be true. How would I graph the function, the constant function, f of x equals 5? Is just a nice straight horizontal line with a height of 5. There's my graph of f of x. And what is the slope at every point on that line? A horizontal line has slope 0, so the derivative function will look like just the x-axis, which is my f prime of x, which is constantly 0. So the derivative of a constant is 0. Here it is stated more generally. If c is a constant and f of x equals c, then f prime of x equals 0. Here's a little proof. Let f of x equal c. C represents some number, some constant. Then by definition of the derivative, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. But f of anything is c, so that numerator, f of x plus h minus f of x, that's really just c minus c. And what's going to happen there? That numerator goes to 0, that whole fraction becomes 0, and the limit as h goes to 0 of 0 is, of course, 0. All right, let's look at something a little more interesting, the power rule. This will be very helpful to us. So we've already seen 3 derivatives. We proved these 3 derivatives using the definition of the derivative. We proved that the derivative of x squared is 2x, and the derivative of 1 over x is negative 1 over x squared, and the derivative of the square root of x is 1 over twice the square root of x. What's the pattern? Well, look what happens if I express each of these expressions as x raised to a power. So the first one's already there. X to x squared is 2x. How about this one? 1 over x. That's the same thing as x to the negative 1. And negative 1 over x squared is the same as negative x to the negative 2. So dividing by x squared is the same as multiplying by x to the negative 2. And then with the square root of x is really the same as x to the 1/2. And this other expression on the right, 1 over 2 root x, is the same as 1/2 times x raised to the negative 1/2. Now there's a pattern. Maybe you can see it. The pattern looks like this. The derivative of x to the n is n times x to the n minus 1. And this works for any n. What is the derivative of x to the 3/4? All right, well, my rule says whatever that exponent is, bring it down out in front, so 3/4. And then my new exponent is 1 less than the previous. So the original exponent was 3/4. If I subtract 1, I get negative 1/4. All right, and if I have the derivative of x to the negative 20, that is going to be negative 20 x raised to the negative 21. All right, here are a few problems for you to try. Apply the power rule and see what you get. Please pause and try the video. Then, when you're ready to check your answers, start the video up again. Okay, let's see how you did. The answer to the first one is 7x to the 6. For number 2, negative 8x to the negative 9. Number 3, 1/3 x to the negative 2/3. For number 4, you have to re-express the original question. It was given to you as 1 over x cubed, so we have to rewrite this as x to a power, x to the negative 3. And now you can find its derivative, negative 3x to the negative 4. The derivative of x is just the derivative of x to the first. Apply the rule, you end up with 1. And the fifth root of x is like x to the 1/5. So when I take that derivative, I get 1/5 x to the negative 4/5. How about a proof for the power rule? Why does that work? So I'll go through this quickly. You don't have to memorize this or even write it down. I'm not going to ask you to reproduce this, but it's interesting to look at. I think it's worth seeing the proof for the power rule. Let f of x be x to the n, x to some power. Now remember, here's one of our other ways of giving the derivative. F prime of a is the limit as x goes to a of f of x minus f of a over x minus a. And so by putting my function in, x to the n, I get the limit as x goes to a of x to the n minus a to the n over x minus a. Now, there's an algebraic fact which is not well known, but it's true. I can factor that numerator. That numerator factors. I can factor out x minus a, and then all this other stuff remains as the other factor. I have an x minus a on top and x minus a on the bottom. All that remains is that other factor. So now, do you see, look how the pattern is. It's x to the n minus 1, x to the n minus 2 times a, and the powers on x go down and down and down. Eventually I get x to the 1 and then no power of x. And the powers of a increase. I have a to the 0 power, a to the 1 power, up and up and up, a to the n minus 2, and then a to the n minus 1. What's going to happen now if I take this limit as x approaches a? X will become a, and I end up with a whole lot of a's raised to powers. In fact, how many terms do I have? If you count carefully, there are n terms in this summation. And what does each term evaluate to? A to the n minus 1. Well, let's see, a to the n minus 2. Oh, that's also a to the n minus 1. This becomes a to the n minus 1, and that's a to the n minus 1. So in fact, I have n different terms, and they all evaluate to a to the n minus 1, so I get n times a to the n minus 1. Well, look at that. What I found was f prime of a equals n times a to the n minus 1. So let's just take out the a, replace it with x, and there you go. F prime of x equals n times x to the n minus 1. I like going through this proof because it really shows us that these rules that we learn, these quote tricks that we do to find the derivative, they really come from the definition of the derivative. I had to use the definition of the derivative to make that rule work. All right, another rule, the constant multiple rule. Here's an example. If I take the derivative of 5x cubed, well, that's not really a power rule because I have that extra 5 in there. The 5 is a constant multiple. And it turns out that I can just take the derivative of the x cubed part, and that 5 just stays there. Nothing happens to it. And then finally at the end I can multiply the 5 times 3 and get 15. If I'm taking the derivative of 7 times the square root of x, the 7 is my constant multiple. It just stays there. I end up taking the derivative of the other part, and then I can multiply it back in. So in general, the rule says that if c is a constant, then the derivative of c times a function is c times the derivative of the function. And we can do a very quick proof for this one too. So this isn't too long. Let's suppose I have a function g. I'll rename my g as c times f of x. Now I want to take the derivative of g and see what I end up with. Well, by definition, the derivative of g is the limit as h goes to 0, g of x plus h minus g of x all over h. What is g really? It's c times f. So c times f of x plus h minus c times f of x. Oh, but then I can just factor out that c. So I have the limit as h goes to 0 of c times that fraction. And here's where I can recall our limit laws. We had a constant multiple rule for limit laws. The limit of the constant times a function acts like the constant times the limit. So I can pull that c out because of limit laws. And now what is that expression? That is exactly f prime of x. And so this proves the constant multiple rule. The sum rule. It turns out that if I have a sum of two functions, x to the fifth plus x cubed, and I want to take the derivative of the sum, the answer is the sum of the two derivatives. If I have 1 over x minus the square root of x, and I want to take the derivative, it just becomes the derivative of the first minus the derivative of the second. The general statement says the derivative of f of x plus g of x equals f prime of x plus g prime of x. And I won't go through a proof of this, but it kind of goes along the lines of the other proofs that we've seen. We end up using the sum rule of limits in the proof. And lastly, the derivative of e to the x. So this kind of has a different character. E to the x is not a polynomial function like everything else that we've been looking at, but it turns out that the derivative of e to the x is e to the x. And I won't give a proof of this, but I'll show an interesting picture. Okay, so this is a generic exponential function. On the top right, you can see f of x equals 1.59 raised to the x. And I can change the base. I can make a larger base or a smaller base, even a base that's between 0 and 1. And so this is a family of exponential functions. And I can show the tangent line at 0. The tangent at x equals 0. And again, I can change the base, make the base larger, smaller, and we see how that tangent line changes. So now I'll do one more thing. Let's show the derivative function. And you could think of the derivative function as just a way of plotting out all the slopes. So for example, as I've got it plotted out right now, the slope of the original curve, the green one, the slope of that guy at x equals 0, the slope of the tangent line is about 0.6. And the yellow curve, it goes through a value of 0.6 because the yellow curve is the derivative. It tells us the values of the yellow curve are the slopes of the green curve. So that yellow curve looks kind of nice and smooth like an exponential function. And what happens at some point if the slope right at 0 actually becomes 1? It looks like the yellow curve and the green curve match up. They are the same function. And this number, 2.27, that is approximately the number e. So e is that number that makes the slope of the tangent line equal to 1. And it just so happens when when the slope of the tangent line is 1 there, and that's when the function and its derivative match up. All right, so the derivative of e to the x is e to the x. Now, using some of these basic rules, we can tackle a function like this, 9 e to the x plus 7x squared minus 11. I'll take the derivative of that, and I get 9 e to the x. So by the constant multiple rule, I can ignore the 9 and take the derivative of e to the x. I get e to the x. Plus, now for this next part, the 7 stays there and the 2 comes down, so I'll get 14x. And then the minus 11 just goes away to 0. So in fact, that is my answer. All right, so we've just introduced the very basics of the rules. And this is a good place to stop for now. In the next lesson, we will do a lot more computation with these rules. But we've introduced them, we've got a basic understanding of how they all work now. So here's where I'll stop.